Hey everyone, welcome back. We heard some great talks before the break about stellar mass black holes in AGN disks. And so this session is meant to be a discussion session where we get to raise some interesting topics and go into things that people want to talk about. Priority, as always, to folks who do not have a PhD. So ask those questions, you know, and let us know. So the way we have this sort of structured right now is we're going to try and, based on sort of slides that we've gotten, we're going to go through sort of, can you form binaries in AGN disks, or do you have to rely on binaries that come from the nuclear star cluster? Is there missing physics involved? Are things merging? And are there observational tests of all of this stuff? So the theme of this conference is all about building bridges. So let me build some bridges right here, right? So to the protoplanetary folks and the stellar folks, we've got a bridge that reaches out to you because we are also thinking about some of the same problems, right? Type 1 and type 2 migration, but with an AGN twist, right? We're thinking about close encounters and mergers for LIGO. But we're dealing with the dynamics in gas, which can, as we've heard many times, both soften and harden binaries. The difference between protoplanetary and protostellar disks, in our case, is that obviously the embedded objects are stars and black holes, right? So we can learn by analogy from protoplanetary disks, but there's a whole bunch of stuff that we've kind of outlined, questions that we can sort of go into and we can talk about. We can also learn from AGN disk simulations. But we can also give those folks a problem, which is that there are embedded objects in those AGN disks, as Savik said yesterday. And so that's going to change how your disk behaves, right? So that's going to be a problem for people. We can also learn from supermassive black hole binary simulations, but unlike the things that we've been seeing where you've got a nice central binary, now we have a binary embedded in a shearing flow. And the gas mass is much larger than the embedded binary. So these are sort of some of the basic parallels and problems that we sort of wanted to outline, bridges that we want to build to the various communities here. And of course, across those bridges come all of the problems associated with all of those areas, all into one place. So AGN are a really fun area to basically tackle all sorts of interesting physical problems. And there's a lot of work to be done. All right, Hui.
Okay, so move right along. For those who just drifted in, we kind of want to, based on the input, focus on three things. The first one will be formation. There are some I guess when I talk to observers, do you ever see a binary black hole merge in the AGN? Do you have any signatures? Nobody told me they've definitely found one yet, but there's a big, there are a large number of uncertainties, like what kind of objects do you actually sustain in an AGN disk, right? There are ideas about their massive stars or never dying stars or single black holes, neutron stars, massive stars, and some do binary. Do they actually migrate? Because out of the protoplanetary community, the disks are not as turbulent, whereas in AGN disks, where everyone believes there's MRI, the radiation physics is very, very important. Radiation physics is also dominating. Do they actually migrate like the way we think they do? I'm not sure we actually know that answer. Then dependence on properties, right? Whether they're eccentric object orbits, mass ratio, spatial distributions, and what signatures, or I hear that we might rely on pre-existing binaries, nuclear star cluster. So we had a couple of contributions, kind of specifically looking at a binary formation issue. Jaru, you wanna? Do you wanna? Yeah.
That should work.
Thank you.
This is a pointer.
Oh, okay. Thank you. This is Hui Li. I'm a graduate student at Cornell University, and also I'm a graduate student at Los Alamos National Laboratory as well. So I just want to bring back the question that Dawn mentioned a little bit this morning about how do we form binary black holes in AGN disks from close encounter between black holes that are initially just single. So in my picture, so at least the picture that I can imagine is this whole process can be generally divided into two steps. Number one is we want to bring separated black holes to much closer distance, and that can possibly be done by migration or migration trap that has been discussed yesterday, for example. And the next step is when they're very close, those two black holes tend to have very large relative kinetic energies. So we need to come up with a mechanism that will be able to dissipate those extra kinetic energy very fast and to a significant amount. So here I include some plot from our, how do you use the laser pointer? Oh yeah, here I include some plot that I actually just took from the paper that we just submitted. In a way, just to kick off, to think about what kind of mechanism that might be important and might occur in this process. So I'm showing here is when we just run the n-body simulations, of two black holes on dynamically unstable orbits, then they will just keep close encountering with each other stochastically. And we find out that in this stochastic process, the minimum separation during close encounter between two black holes actually follows a very, I would say, very accurate power law functions. The only parameter that seems to be matter is the initial inclination that we give to the system. But what we get from here is that we know, well, close encounter can happen at all different ranges, at a very broad range of minimum separation. By minimum separation, I mean the paracenter distance, so do not be confused with the sine major axis of a black hole, because all these close encounter are very eccentric, tends to be parabolic. So that's why in our paper we look at, is it possible to use gravitational wave to form binaries or just form two merging black holes? So we're looking at these ends. But I want to say that because of this, we can look at all the possibilities as for RP over RH on this range as well. And with this distribution, we know how likely that each of these processes is going to happen. Yeah.
You want to just summarize the result rather than the details? Yeah.
Okay, cool. Yeah. So I just want to say this is somewhat a robust distribution because at Los Alamos we have a tool to do some real hydro simulations of 2D disks and putting lots of black holes into the simulation at the same time, and we find the same distribution. And this plot is something about very preliminary result that we get. We look at if it's migration trap and what we need to think about more carefully in the migration trap as well. This is just some type 1 migration simulation with 2D hydro, and we see that the eccentricity of the black hole, which should be excited through close encounter, becomes quickly damped. So in a way that if the disk parameter is not set up properly, we can actually diminish the number of close encounter we have because the eccentricity becomes so small. And sometimes we have this 1-to-1 resonances. So all these things are things that we need to keep in mind when we think about what can happen if you want to use a disk-assisted process to form binary black holes. But yeah, that's just to kick off and just to give some general direction that I think we can go. Yeah, that's it. Thank you.
Any comments, questions?
Yeah, I just have a quick question. So it looks like you start with 11 and then you end up with 6 in that. Am I interpreting the graph correctly?
11. And here's
scattering. So some of them are scattered out. Oh, right.
Oh yeah, thank you. So it's actually not scatterings. We started with 11 because we can see all 11 of them because we started with initial separations. But here, due to the convergent migration, many of them ends up in 1-to-1 period ratios. Therefore, they have the same R. Actually, sorry, this RP is different from that RP, my problem. This is the distance from the supermassive black holes. So you can see, if you look very carefully, this magenta curve and this orange curve, they overlap on top of each other. This is just how fast the migration is that brings them into the 1-to-1 orbital ratios. They have the same R coordinates from the supermassive black holes, but they're not binary because they're just separated far away in a azimuthal direction.
Got it. Thanks.
Can you just clarify how you got the eccentricity damping from this plot? Or from this result? Or is that something that you assume?
Thank you. I'm sorry if I didn't say it clearly. We're doing hydro simulations with planet put inside. So the planet actually, it's being run at the same time. We have all the effects from the disk onto the, black holes calculated on the fly at each step of the hydro simulation. So it's just disk will damp the eccentricity.
Can I ask one while I'm on the way to Enrico? What is RG over RH for a typical case here?
RG of the black hole that we do in these close encounters.
Yeah.
Here in this case, we considered black hole mass that's around like 10 to the.
Just give a number.
Oh, okay. I think it's somewhere 10 to the -5, if I remember correctly. RG over RH. Or maybe smaller, if I remember correctly.
Yeah, I was wondering if we can maybe just frame it in the following way. So the LIGO rate is about per galaxy, like 10 to the -5 mergers per galaxy per rate. So you need about, on the history of the universe, you need about 10 to the 5 black hole binaries. So, and if you think about what star formation are you tapping into, it's relatively close to the AGN. And I wonder when people think about rates, is like how much flux of black holes you have to get from significantly further away from the sphere of influence to go in to get a rate of about 10 to the -5 per galaxy, and if that's tangible or not.
Yeah, that's a very interesting point, and thank you. Right now, we're just doing some scale-free simulations, and we have not implemented any population synthesis analysis inside to think about what would be the rate getting out from this. Also, I think if we could get it properly, that's why we need to consider all the possible short-range effect can happen in this region instead of just the gravitational wave that we're getting, because that would be clearly, I hope it's just going to be an underestimate if we consider very small, very short interactions. Yeah, that's why I bring this question up, because I think lots of things that can happen in this part, and that can change the number that we estimated dramatically if these are possible. Thank you.
So yeah, I can just comment. In our toy model with Tagawa, we have a prediction for these rates, but very uncertain. But it's a prediction in the sense that the outer region of the disk is included in the so-called Thomson quartered Murray model. So we form the stars and the remnant black holes and let them migrate. And those give rates which are at the low end of the LIGO rate. So I don't know the units I remember are few per cubic gigaparsec per year. So those rates are maybe comparable to a non-negligible fraction of LIGO events. Probably hard to do all of them. I have actually a question which is more broad and which may relate to this rate, which I think is the rate prediction, or how many you form. The biggest question I think from these talks is whether this. I think you only actually form a binary in very rare cases when they pass close to each other, whereas we assumed, we actually adopted the idea from the Kuiper belt formation literature, where the idea is that when two small bodies pass each other, and if the dynamical friction on the background dissipates the binding energy during the Hill sphere's passage, then you bind it. So we assume that in our model. So I think your rate might be lower if you assume only a small fraction get attached. But my question, which is much more broad, is maybe to Donglai also, why is that thinking not valid? So I would think dissipation in general is the key to capturing binaries. which is what we assumed, but we didn't show it.
Yeah.
But I thought that was the key.
Yeah.
You want to remove
Yeah.
their relative velocity and make them bound. Without dissipation, it's a reversible problem. You don't actually ever form a genuine binary.
It is a reversible problem, but the direction which it's going is not clear. So the numerical experiment that Jialu did, this paper, this paper quoted here in the last section, we put it last because it's not reliable because we don't believe this frictional force thing, right? Which is what this KBO thing put in. But anyway, the dissipation does not help.
Maybe a quick clarification. So the only ones that form binaries in this plot are like the lower left, which are within 10 minus.
Yes.
Right?
So if I understand what Jialu said here is that putting all this hydro does not help also, right? You didn't get any merger, additional merger, right?
Well, if I may inject, so the hydro simulation we're doing is 2D, and we haven't, in those runs, we have the rebound, like the close encounter treatment, but we didn't resolve the CSDs very well. So the next step is to resolve the CSDs better, so that will hopefully introduce more dissipative processes.
It's not captured. That CSD is not captured in this KBO formation theory. I still need to digest this Goldreich-Sari paper, and anyway, I don't want to say. I think that's
but yeah. I think that this is a possible project to work on that would look at a hydro to look at more close encounters.
I'll just follow up. I'm not sure if maybe people are familiar with, there's literature going back to, I think, the mid-90s. Matthew might be able to correct me on this, but of sort of disk and star disk encounters in isolated environments. So there was some work led by Nick Mokel and John Valley. That was in the late 2000s. There was some work by Yves Ostreicher and then Diego Munoz in 2014. So in many cases, that doesn't help with capture. And now ignoring it being in orbit around an AGN, I'm not sure that really matters. So I guess I'm saying people have done these calculations in other environments, and it would be, I think, straightforward to apply it here. But
it actually might matter because of the tidal forces from central.
Yeah, that may change. I mean, certainly if you get the orbits right, and it may give you better preferential alignment to get certain cases, but it's still not a super efficient process to produce capture.
Mm-hmm.
Just in the star formation context, so Caitlin's right. There was some work done in the 1990s, like Kathy Clark and a PhD student of Kathy Clark, Simon Hall. That was 1996. One of the issues in star formation that Kathy found early on was if you think about capture of stars in a star cluster, the problem there is your relative velocities in the star cluster are so high that you tend to just destroy any disks without actually capturing into binary systems. So it really does matter a lot about the velocity dispersion between the things. Now in the AGN disks, the velocity dispersions, I would imagine the relative velocity dispersion is probably a lot lower. So actually the disks might help you.
That's right.
More than in the stellar case. So I mean, Caitlin's right. You should certainly look at the stellar stuff that's been done. But I think this might be more favorable to capture than in the stellar case.
My question's kind of going back to the rates question. So is it possible to, has someone looked at evaluating the rates from progenitor population perspective? Like how many massive stars go into the AGN and then how long does it take to form? I know there's a lot of theories around this.
Yeah. So your question is basically what role does star formation in the AGN disk play in the rate that you expect? No, sorry. Okay, no.
I think I understand the question. So, I mean, we've taken estimates of what the nuclear star cluster stellar mass black hole population might be, which is obviously based on other folks' work on star formation, but also infall, right? So some of the nuclear star clusters, black holes, are probably coming from globular cluster infall. And so if you take some maximal assumptions, right? So this was actually in 2018, we had a paper where we said, all right, let's take some extremal assumptions for all of these parameters. Like what if you just say, write down a Drake equation, what should the rate depend on? And it depends on a handful of parameters, and we can, know some of those parameters, but most of those parameters are unknown to a couple of orders of magnitude. So you just take all the extremal values and you say, what's the worst case? What's the best case? And you get somewhere between 10 to the minus 4 per cubic gigaparsec per year and 10 to the 4 per cubic gigaparsec per year, which is super unhelpful, except that it's not, because you can immediately do some astrophysics with it, because whatever you need to get 10 to the 4 per cubic gigaparsec per year is obviously not the universe we live in, because LIGO already says the upper limit to the rate is way lower than that. So those are some extremal assumptions, and there may be some somewhat inconsistent things, like you couldn't actually get all of those all the way up to 10 to the 4 because you have, you're just taking each parameter in isolation as opposed to making a self-consistent picture of our universe. But some of the things that matter the most are, what's a typical stellar mass black hole population, because you have to have them there. And then also, what is the typical lifetime of the AGN disk? So this just came up at coffee, and I think this is kind of an underappreciated factor. So whatever you have at the start of the AGN phase, right? If you have a nuclear star cluster and you assume that in the next instant it turns into an AGN, then even if you make no new binaries, the binaries that are there, if the gas has the effect of shrinking their semi-major axis on very short timescales, then you get a burst of mergers, right? But then whatever you've done, you're done, right? Especially if you can't form any new binaries. Maybe you can form new binaries, but even so, at some point, in a lot of interesting, exciting, dynamical things happen in short time scales. So as soon as you turn the AGN on, exciting things happen. But if you let it live for 100 megayears, all the exciting stuff happens in the first 10 megayears, and then nothing interesting happens. And so you get a very different rate. We know what the AGN fraction is observationally, as long as we all agree on what constitutes an AGN, which is another argument, not for here. But if you have a dynamically important disk, then if you turn it on more times, right, you know that the total lifetime, if you take an AGN fraction, you say the total lifetime for each galaxy in an active phase has to be 10 to the 8 years, but you can't tell a priori whether that's one phase of 10 to the 8 years or 100 phases of 1,000,000 years. And those are very different consequences in terms of like how many mergers you might get out of that system. And so if you don't have some independent measure of the lifetime, then there's a lot to play with there. And so some of the different estimates that people have gotten, the very wide range of rates, I think that that's actually the thing that drives it the most. And I think it's underappreciated because it's often a hidden assumption. So a shorter AGN lifetime produces more mergers, which sounds weird, but it's true.
Thank you. I think in the interest of time, we may have to move on. So the next topic that we got input on was, to merge and not to merge, right? So this is a plot I actually adapted from Doug Lin several years ago. So he plotted, around the 10 to 8 solar mass black hole, the celestial radius is about 10 to 13. H of R is anywhere on the order of 10 to the minus 2 or 10 to the minus 3. So if we put a binary black hole around 1,000 or 10 to the 4 RG, we're looking at 10 to 16 or 17 centimeter for R and 1% of that for H. So if you have a stellar mass black hole, 10 solar masses, you're looking at 10 to the 6 centimeter. So that's 10 to the 10, which is doable. That's supposed to be a joke, but nobody laughed. So that you put in the binary. So a lot of the talks we heard today is kind of looking at this scale, right? So several of us, including this morning, we're looking at on the order of H and RH, and then we may go down by a factor of 100 to 1,000. That's kind of stops here. But then we need to do all the way over here, and then you have accretion going on, presumably, hopefully, that would have jets and winds radiation and push it all the way back. And we've got to cover this whole range. Now, so the large number of questions tied to some of the discussions this morning. If the accretion rate is HyperEddington, because if you take the AGN M dot and try to put it onto this tiny black hole, that's just, overwhelming what's going to happen. And there's interesting lessons from GRB community and also AGN jet. Obviously, GRBs are surrounded by a huge stellar atmosphere. Nonetheless, it makes gamma of 1,000 but depending on the model, will be even higher. So what's going on there? Would the radiation significantly modify CSD, like Adam mentioned this morning, that whenever you puff up the CSD and heats it up and you weaken the torques within the CSD, the CBD torques will try to drive them in. So that's good news in terms of merger, but it's not really true. How much physics can we actually do? And generally the feedback, how do you reach all the way back to the RH? One key difference between this environment and the typical AGN environment is that you always have a AGN disk background, which presents an optical depth to the radiation that's significant. Whereas the other models may not be, the other systems may not be true. So Yanfei, I know you are rushing, so maybe you want to say a few words on some of the GRMHDs.
I will be very quick. I need to go to pick up my son in 2 minutes. Just give one example, mention about the effects of radiation. So here is a work in progress. If you compare a simulation mean disk from the here radius injected stream from L2 down to all the way to the ISCO for one of the black hole. So in the left panel, I show you pure MHD simulations of the disk formed from the stream. On the right-hand side, I show you the simulation with the full 3D radiation MHD. The accretion rate from the stream is way above the antenna accretion rate. And then you can see the big difference between the structure of the disk. One obvious thing you see that once you turn on the radiation, the power dissipated by the accretion basically drive a strong outflow. And also the disk is much more extended compared with the MHD case. And you can also look for the actual variability from the mean disk and the angular momentum carried by the outflow that leave the system, which is almost zero in the MHD case. Just an example to show you what you can do by including the radiation physics. Now I need to go.
Questions, comments?
Sorry, I just want more information. This is Scott Noble. Yanfei, what kind of thermodynamics did you assume in the 3D MHD runs? Did you cool the disk or?
Yeah, the 3D MHD is locally isothermal, so with a fixed HOR. Yeah.
This could be very quick, but how is the fact that you're feeding through the stream make it very different from your earlier similar simulations where you had the torus, super-Eddington accretion by a torus for a single black hole and no shear flow? Is the fact that it isolated versus this one, is it very different in terms of how much wind, for example, what fraction of the m dot goes out in the wind?
The gross property is not that different, but the stream does provide a perturber to the disk. You actually see the outflow is a time vary because of the periodicity introduced by the stream. This is also a much nicer experiment because the stream provides much more realistic initial conditions compared with the pure torus typically used in the isolated AGNs.
Yeah, Mark Avera, it's really cool simulations. What is the space-time here? Is it, do you have a perturbing secondary black hole, or is it?
This is the mean disk in a binary system. So we include the tidal potential from the companion, which is not included in the grid. So this is in the rotating frame of the binary. And the spherical polar coordinate is centered on the smaller object. Because again, you need to choose that the choose 3D radiation MHD expensive, but you can do something to zoom in to these small scales and learn some physics.
That's that. Jan Fei, go and get his kid. Thanks, Jan.
Sorry, well, you know how to find him, but
yeah. Yeah, I actually wanted to ask Yan Fei, maybe somebody can fill in for him, but what is the Eddington ratio? Maybe he mentioned what the Eddington ratio was here.
I was going to ask him that, but he left. So no. Okay, so maybe probably we just
HyperEddington. That's what
if it were HyperEddington, then we were wondering why isothermal, not adiabatic with polytropic index of 4/3, because that seems like it would be more appropriate. But if it is around Eddington, then it makes sense because then there would be radiative cooling. Right. Except that disk looks like it is like blowing so much, and it's not very thin on the right with radiation MHD. So it would seem to me that it would be quite a bit super Eddington just from the picture. Thank you.
Yep. Okay. We have to end in about 10 minutes, right?
We have 10 minutes?
Yeah, so maybe we should, maybe you want to, so we get one contribution, something you want to?
Zoltan, do you have a mic?
Hi, this is Zoltan again. So quick, I was going to say there's a problem which is shoved under the rug, but it's actually no longer under the rug because it was mentioned several times that these stellar embedded black holes accrete at such high rates. And actually that causes really that causes two problems really. One is, so the bottom left panel, if you want to actually look at it, is just a prediction for the Bondi-like accretion rate for a point mass in the AGN disk. And on the upper left, you can see it's 10 to the 4 times Eddington. So this really is two problems. One, this means the stellar mass black hole would quickly become a supermassive black hole. And that's problem one. Problem two is we couldn't have quasars because you would steal all the fuel if you had a few dozen of these in the disk. So this really needs to be addressed. I think one possibility is what Yan Fei just showed. Radiation blows out most of the gas, doesn't accrete on the black hole. I think it may solve the problem one, because then the stellar mass black hole won't grow so fast. But if the wind leaves the system, then you still stolen the fuel from the quasar. So it's like a shower head. The disk becomes a bunch of small black holes spewing out most of the mass. So that's also, well, I don't know, that it's a question mark. It's a question for Yan Fei. What is the wind velocity? So it's possible, but the wind would have to be strong and would to not allow the feed growth of the hole, but would have to be not strong enough to eject the gas from the, unbind it from the supermassive black hole. So another version, which is our paper to be advertised number 2, which I think is actually an answer to Adam Dempsey's last slide. Is Adam still here? Yeah. So I don't know. We basically made a cartoon model of this scenario where you have a stellar mass black hole being fed at super Eddington rate, blows a jet turns on. There's a cocoon created by the jet, which is overpressured and feeds back on the outer parts of the disk. So wherever the ramp pressure from the disk rotation matches the pressure of the cocoon, the disk is blown out. And then the rest of the disk can accrete. And then there's vacuum for a while until the whole thing refills again. So this is an episodic accretion scenario caused by the jet feedback in this cartoon model. Should be turned into a question to the audience.
You put the jet in
is this something you can simulate rather than relying on these toy models.
So do you put the jet in by hand, or do you, I don't know, how do you launch the jet?
No, so actually tie the jet's power to m dot. So there's an m dot coming in from the Bondi like m dot.
Okay. So I guess we would have to check in the larger scale simulations if you get the right conditions on large scale, like through the MRI stuff or the B fields to launch the jets.
I'm also interested in whether the radiation feedback people think is viable or not.
Yeah. Zoltan, a question about how you did the calculation in that paper. And that is, basically, you're using this small black hole as an energy source in a portion of the disk. How does that energy release get spread through the adjoining disk? And essentially, how much of it does it affect? Do you do radiation diffusion? Do you look at the progress of mechanical luminosity? How do you actually describe it?
We should probably discuss offline, but yeah, the energy is injected and makes a chimney. It ejects a lot of the AGN, a column of the AGN disk.
Yeah, because I think it seems to me that there's should be a fairly simple scaling criterion in terms of how much energy you can release from that local black hole without overcoming the ordinary disk dissipation rate within the affected region.
Okay, we should.
Yeah, maybe
you know,
Sasha had his hand up for a while. Go ahead.
So
quick.
We haven't simulated this, but what we've done instead, we've said, let's put the black hole into a uniform medium. Let's give it some rotation, which is kind of here, you have a shear, right? So you kind of have effective local rotation, and let's see what happens. And what we find is that when the jet shoots out, it doesn't completely evacuate the whole thing. It can't, it only shoots up and down, but it suppresses the mass accretion rate by like a factor of 5 or so. It's pretty typical. We don't quite understand why it's 5. Maybe that's the sort of solid angle fractionally that's occulted by the jets and the cocoons. But we find it in like various contexts, like collapsing star or the collapsing galactic material. I think this is a really interesting case. We should probably talk so that we can simulate that.
In condition left side, density is less here.
Yeah, we can.
Density is less. I think might be easier to, but make an actual cavity. I think we actually do need a relatively large cavity in order to help solve our overfeeding problem. Otherwise, the factor of 5 doesn't really help.
Well, let's talk more about this. Thank you.
Enrico, then Elena, and then we should move on.
Yeah, I think going back to Julian's argument, you know, with the rate, the LIGO rate, let's say that it's 10 to the minus 5 per galaxy per year. So that means that you have to compete with about 1,000 supernovae at least. And then one of the issues that it goes against you there is that because you have a scale height of the disk and you have such a pressure gradient, it's very difficult for the energy to be shared with a significant fraction of the disk. So anyway, that balance is interesting. It's kind of like the baryon loading factor of one of this compared to, you know, 1,000 or 10,000 supernova. In other words, which one is more effective to regulate feedback in the systems?
I'm forcefully moving on because we do want to get to this possible. We can talk about theory all we want, but we need the signatures.
Yeah, so one of the ironies of this channel, right, is that you have black holes who are surrounded by gas and they should give you an EM counterpart. One of the ironies is that you may never see such a counterpart, right? That's the problem. AGN are fundamentally really bright. You know, stellar mass black holes by comparison are not going to be that luminous. And so you need definitely a strange combination of events to get something that you could see. So if your merger happens in the gas midplane, you're never going to see it. That's step one. Step two, if your black hole is kicked out of, you know, if your binary black hole is kicked out of the AGN disk, then it needs to be bright enough to show up against your AGN. Maybe in some low luminosity AGN cases, you know, if you're lucky. But But you also need to be able to distinguish whatever that bright enough thing is against whatever is going on in the AGN in terms of regular variability or things going bump in the disk, like supernovae, which we'll hear about in just a sec. Maybe there are things we can look for. So we have to search, right? So if you don't look, you won't find anything. It doesn't mean we will ever see anything, but we should at least look. Maybe we see the occasional weird flare. That doesn't convince people, so we should go with a statistical argument instead. And so that leads us to Niccolò Veronese, if we have a mic. Yeah. Yeah, good.
Thanks. Actually, I think you can go directly to the second slide.
Second slide,
yeah. Then if someone wants to talk about the predictions for 04, I'm here. I'm the one with the pink shirt, so just come. So yeah, as Barry was saying, I think that one of the options that we have in order to investigate this AGN gravitational wave, binary black hole connection, is to zoom out from the disk itself and look at the presence or absence of a spatial correlation between AGN positions in the sky and gravitational wave localization volumes. So this is what we have done. And so we implemented this likelihood ratio method based on the paper from Imre Bartos, Zoltan Hyman, and others from 2017. And so one of the main results we got is here in this plot. So on the x-axis, we have the fraction of gravitational waves that come from AGN, while on the y-axis, you have on the left-hand side the number density of AGN we consider, and on the right-hand side the bolometric luminosities that, choose what you like more. So on the right-hand side of the dashed white line that you should see like going across the plot, basically we have the region of this 2D parameter space in which we can actually test these gravitational wave AGN connections with the 13 detections that we have done with LIGO and Virgo interferometers during 03 below redshift 0.2. So this is something that we can actually already do. More specifically, on the right-hand side, we have the region of this 2D parameter space in which we can reject, we have the chance of rejecting the no connection hypothesis with a 3 sigma significance for the dashed line or 2 sigma significance for the solid line. So this is something that we can already do, and this is actually something that we are already doing. So going from simulations to actual gravitational wave sky maps and actual observed AGN catalogs. Of course, this passing comes with its challenges. But the thing is, so here comes the question that I wanted to ask. So we see that one of the 2 parameters we play with, it's the AGN number density or luminosity or mass of the central supermassive black hole. My question is, can we expect a correlation between these observables of AGN and the characteristics, for example, the masses of the components of stellar mass binary black holes within the AGN disk? This is what I wanted to ask. Thank you.
Questions?
I'm not sure I actually fully understand your question, so I just want to see, and maybe we can chat more offline and other folks may have thoughts, but so are you asking if there is a correlation between the properties of the binary black hole mergers themselves that would be LIGO detectable and the properties of the AGN, for example, the mass of the central object or its luminosity?
Yes, that's the question.
Okay.
And if we can infer some connection, because this would be incredibly interesting from the statistical point of view of modeling the correlation.
I think other folks may have thoughts, but I will say that it's not obvious to me that there would be a characteristic. of the mergers that is related, apart from perhaps the number, because naively I would expect that the AGN disk size scale might scale to some extent with the mass of the central black hole. The luminosity might have something to do with the density, for example, and but the raw materials would be some IMF that would maybe be theoretically universal. So, yeah.
Yeah. So from the theoretical point of view, I thought that there may be a correlation between the AGN luminosities. Say, the more massive the black hole, the bigger the potential well, and so you have the chance to have hierarchical mergers, and so on average, expecting more massive black hole binaries. For instance, this is, and we are curious to know if there are other theoretical predictions that can link the observable properties of GW detections with the observable properties of AGNs that we can test.
Okay, okay, Enrico, you get the last word.
Okay, Enrico Ramirez Ruiz. I was just wondering, this is interesting, if you take into account the orientation, I mean, if you have a galaxy catalog and you have an orientation, how many of them are face on? Those are going to be more likely just, and I wonder what's the number density as a function of orientation.
I was told we were out of time, just maybe 5 seconds, that there are supernovae explosion calculations in AGN stratified red hydro simulations. So for those of you who are interested in this topic, please come talk to me. This is work done by Chris Fryer and others at the lab. They basically find that they got a very different type of supernovae when you put one of such explosion 10 to the 51 Earths inside a AGN condition. You actually get a rise about a 10 to the 5 seconds, and the brightness goes up by about a factor of 100, and it peaks in the UV and EUV, not X-ray. So here are some of the possible implications for observing such transients over days and weeks. So that's something I think will be also very, very interesting to make predictions for supernovae explosion as well as jets that's trying to plow through such an optically thick regime to get the signature. Yeah.
Okay. Thanks everyone who participated. Thanks all for having a really great discussion.